Alright, so we're going to be going through a beam design example here, and this is our particular scenario here. We have a live load of 790 pounds per linear foot, and then also a dead load of 300 pounds per linear foot. The beam length is going to span 18 feet, and we've also got an FY value that is equal to 50 kips per square inch. And one of the other things for the criteria for the beam is we want to really focus on choosing the lightest wide flange steel section. So let's go ahead and let's write down some information here. So what we've got here is an 18-foot long beam, and so we just did a little model here of the beam. This is going to be reaction support A, reaction support B is going to be here. The distance between these two reaction supports is going to be 18 feet. Now additionally, we're going to have two uniformly distributed loads, and so we're going to have the live load as well as the dead load. And so we can go ahead and put in here, the two uniformly distributed loads. So we're going to go ahead and represent the other uniformly distributed load here in blue. So both of these are going to be acting on the beam, right? And so now we got to go back in here and we got to write out these values for these. And so the live load is 790, the dead load is 300. And so we can put dead load, WDL, that's going to be equal to 300 pounds per foot. And then we've also got the uniformly distributed load that's going to be coming from that live load. And because that one's greater, we've got it going higher up. That's going to be the 790 pounds per feet. Okay. So both of these are going to be uniformly distributed loads that are going to be acting on this beam. We're going to end up using these to actually determine out the reaction supports as well as the shear force that's caused by these. Okay, so let's go ahead and let's get ready to begin. What I'm going to go ahead and do is I'm going to write down some criteria here. So this is the criteria for our beam. First off, we want to choose the lightest wide flange steel beam. Okay. Second thing is we need to support a live load that is going to be equal to 790 pounds per foot, and also a dead load that is going to be equal to 300 pounds per linear foot. Okay, so now in terms of that span or the length, we can also write that down. So the span or the length of the beam, it's going to be equal to 18 feet. We're also going to be supporting a plaster ceiling, and so this is going to come down to whenever we determine our deflection, the max deflection that can occur. It's going to be important to know that it's supporting a plaster ceiling. The fifth thing that I want to write down is it's just a given. It's Fy is equal to 50 KSI. Now that is kips per square inch. Now if I want to end up converting that to pounds, this is going to be equal to 50,000. There are 1,000 pounds in one kip, so per inch squared. And we might end up seeing that we might have to come back to this Fy later, and we might have to change some units for that, but we're going to keep it like that just for right now. Okay, so what I'm going to go ahead and do is the following. I'm going to solve first for our reaction supports, and so what we can end up doing, is if you put this into MD solids, you're going to end up finding that the reaction supports, it's going to be equal to these values here that are on the max shear, right? And then also at the bottom here, this minimum shear. But we can also just solve for that as well, just from using our equation sheet. So this is going to be the situation where we have two of these scenario 2 in here, because it's two uniformly distributed loads. If I go in here, I could find the total load, and the total load is just going to be equal to the live load plus the dead load in this instance. So it's going to be that 790 pounds per feet plus the 300 pounds per linear foot. That's going to end up giving us 1,090 pounds per foot for our total load. And so now, given this, we know that we can approximate this as just a single uniformly distributed load. That's 1,090. So whenever I go in here and I use equation 12.4 in our equation sheet, we can end up writing this out. WL divided by 2. So now W in this case is going to be that 1090. We're going to multiply that. So it's the pounds multiplied by the length, which is going to be 18. Divide that by 2. What we end up finding is that this is basically the equivalent of just taking 1090 times 9. And so that's going to end up giving us that value of 9,810, and that's pounds. So that's our reaction. Now, just as we said, if we throw this into MD solids, we're going to also find out that that is the max shear as well. And so this is also max shear force as well, right? So what we can also end up finding is the maximum moment. Now, also provided to us from our equation sheet, we're going to be going with equation 12.5. It states that the max moment is equal to the uniformly distributed load multiplied by the length squared divided by 8. This is going to occur at the center of the beam in this particular scenario. And so we've got this 1,090 pounds per feet. We're going to multiply that by the length of 18 feet. Now that is going to end up squaring that, and then we're going to divide that by 8. So now what's going to end up happening is it's going to be 18 feet squared is what's going to happen with that unit. One of those square feet, it's going to cancel with the feet down here, and so we're going to be left with a unit of pounds multiplied by feet. So now what we can end up doing is we can take 1090, multiply that by 18 squared, and then we can divide that by 8. And we're going to end up with 44,145 pounds times feet, and that's going to be the max moment. Now, just as we were saying in the notes, the max moment, that's also equal to MA as well in the next equation that we're going to end up using. And so just as you can see here, you throw it into MD solids, you end up finding out that your max moment is also equal to that. Also, if you did have the shear diagram, do remember, you can find the area of this shear diagram right here up until this point where it equals 0. That's the max moment. That's how you can also determine what this value is as well. Perfect. So let's go ahead and let's move on. So the next thing that we want to end up calculating out is going to be the actual nominal bending moment here. So just as we said in our notes, the nominal bending moment must be greater than or equal to MA multiplied by the bending moment safety factor. And so if we end up going in here, we can end up plugging in some of these values. So MN, we're going to be solving for that, must be greater than or equal to MA. Now, as we said, the max moment is actually what MA is. It's the applied max moment there. And so that's going to be 44,145. And then this is pounds times feet, it's the unit. And we're going to multiply that by the safety factor, which is unitless. Please do remember, as mentioned in the notes, the safety factor for this course, unless otherwise specified, is going to be 1.67 for our bending moment safety factor. Now, moving on, what we can end up doing is we can evaluate this. So if we now take 44,145 multiplied by 1.67, we can end up finding that the nominal bending moment is this value right here, 73,722.15 pounds times feet. Now, what we want to ensure is that the beam that we're going to end up using is going to be able to withstand a bending moment that is greater than or equal to this value. Okay, so that's just out of safety, right? Although the max moment that the beam will actually be subjected to, given these loads here, although it is just this value, we want to take into consideration that safety factor, and we're basically going to have 167% of this number, right? Just out of safety. So that is for the nominal bending moment. Now, this we can end up using to determine what type of beam we're going to end up needing. Also given in our notes is this equation here, MN, which is equal to Fy times Zx. Now, Fy, that is given to us. Zx, however, if we end up going to this website that we had seen, steel requests, you will end up being able to find, so not in dimensions, but if you click on properties, you can find this value here, which is Zx, which is the plastic modulus. Now, plastic modulus, that is given in cubic inches. Now, if you end up going down here, you'll end up finding for each of these beams, these wide flange beams, there's a specific plastic modulus for those. And so what we want to end up finding is a plastic modulus value that will be multiplied by Fy, and that will end up being greater than or equal to this value of 73,722.15. Okay, and so since we know what Fy is, what we can actually do is we can solve for Zx so we can determine what that needs to be, right? And so what we can end up doing is we can actually solve for these values. So let's go ahead and let's first solve just in terms of variables here. So Mn divided by Fy is going to be equal to Zx, right? Now, in terms of Zx, let's go ahead and calculate that out. So Mn here is going to be 73,722.15. We're going to divide that by Fy. Now, Fy was in pounds per inch squared. Now, as you remember, up here we have this unit of pounds times feet, right? And then if we divide this by a unit that is in 50,000 pounds per inch squared, we're going to end up finding that, we're going to have a unit of, although these pounds will cancel, we're going to have feet times square inches. And so what we want to do is we want to actually convert this up here on the top as well, so that instead of this being a unit of feet, it's going to be a unit of inches. And so what I can do is I can just multiply this by the conversion factor from feet to inches. So we're going to go from feet to inches here, and then now what we're going to end up with is actually a value of cubic inches, which is exactly what we want. And so now we can evaluate this. This is 73,722.15 multiplied by 12 divided by 50,000. So let's go ahead and let's calculate this out. We're going to multiply that by 12, divide this by 50,000. And what we're going to end up with is a value of Zx that is going to be 17.69. Now what I'm going to do is I'm going to go ahead and round that up. And then as you remember, the inches squared, this is basically 1 divided by inches squared, right? And so that's actually just equal to just having square inches on the top. Now that's multiplied by a unit, of inches. And so that's how we're going to end up with this cubic inches. So Zx needs to be at least 17.7 cubic inches. Okay, and so now from this, and I can end up actually setting this up, I'm going to set this up so Zx is greater than or equal to 17.7 cubic inches is what we need. So if we go in here, we can end up finding some different potential options. And so if I keep scrolling down, we'll find that we don't want anything that's going to be of this weight or of this depth here because of just how high those values are. We don't want to end up choosing something that's very, very heavy, right? We want to end up going with the lightest solution here that we could end up using, but we also still need to make sure that everything else is satisfied. So in this case, I can end up writing down some different options. We could end up going with I see a 10 by 17. That's going to be 18.7. So we're going to write that one down. So we're going to try W 10 by 17. And then let's put down one other option too. So we could go with that, or we could go 12 by 16, right? So 12 by 16. Now, I'm not going to choose 10 by 19. Why is that? It's because per linear foot, that's going to weigh 19 feet or 19 pounds per foot. If I go with the 12 by 16, we're gonna end up seeing that the 12 by 16, it is 16 pounds per foot, and the ZX value is 20.1. So the ZX value is actually greater than that of the 10 by 17. So I'm gonna actually go with the 12 by 16, and that's what we're gonna end up using for our calculation. So I'm gonna try the W12 by 16. 10 by 17 could be another potential, but because 12 by 16, that has a ZX value of 20.1 cubic inches, and it's also lighter, I'm gonna end up going with that, okay? The ZX value for our 10 by 17 was 18.7 cubic inches, and remember, it's heavier, it's a pound heavier per linear foot, so that's why we're going with the W12 by 16. So up next, what we need to do is we need to actually calculate out the shear, check the shear strength, and so we're gonna go ahead and do that. And so we're gonna end up using the properties of the W12 by 16, so I'm just gonna write W12 by 16. I'm gonna put ZX here is equal to 20.1 cubic inches. And so now we can begin to go through this and kind of get some information. Now the Vn, so you remember this equation, Vn is greater than or equal to Va multiplied by omega V. Remember, this is the safety factor, and so this is going to be the nominal shear force. So Va is going to be that max shear force, which we end up saying that the max shear force here would be the 9,810. And so what we can do is we can plug that in, 9,810 pounds. We're going to multiply that by our safety factor for the shear force. Now remember, throughout the entirety of this course, we're going to be using 1.5 unless otherwise specified for the safety factor for our shear force. So now what we can do is we can find out what the nominal shear force needs to be. 9810 times 1.5, and then now that's going to be Vn, the nominal shear force, must be greater than 14,715, and that is going to be in a unit of pounds. Okay, so we now know that. Okay, so that's what that needs to be. Now what we can do is we can actually use the equation Vn equals 0.6 Fy multiplied by AW, where AW, remember, is equal to the depth of that particular beam multiplied by that web thickness. Okay, so let's go ahead and write this out. Vn is going to equal 0.6 Fy multiplied by D multiplied by TW. And so what we can do is we can look at this for a actual W12 by 16 beam to find these dimensions here. Okay, so let's go ahead and let's write down everything that we do know though. 0.6, now this is Fy. So as you remember, our Fy value for this is going to be equal to, let's see here, what was that? Perfect. Fy in our case is equal to 50 kips per square inch, which is 50,000 pounds per square inch. And so we're going to end up looking at this, and I will tell you that you might be thinking, oh, this is inches, square inches, we might need to convert. What you're going to end up finding is depth and the thickness, the web thickness, those are going to be in actual units of inches. Okay, so remember, we've got a W12 by 16, and so that's what we're going to end up looking at. We're going to look at the not the properties here. We want to end up looking at the dimensions of this. So what we can also do in here is W, and then we can do 12. Oops, I put EW, so it's W12, and then we've got by, what is that, 16? 16. And so now if I scroll down, we can also just end up kind of navigating this, but it's going to point it out for us here. So we need to find out the depth. So the depth in this case is going to be equal to 11.99 inches, and so I'm writing this down, and then the web thickness is going to be 0.22 inches, 0.22 inches here. Okay, and so if we go to this actual this guy right here too, you can end up seeing what that web thickness is, and so that's that inner part of the Y. That's what the web thickness is. Now the D is just the depth of this beam, so from the top face all the way down to the bottom face here. So we've got that, and so now let's go ahead, let's get back to here. So we can calculate this out. This is that depth, this is the web thickness, and so now we can find out for Vn, we can see if this is going to end up working. So we can take 0.6 times 50,000 multiplied by 11.99 multiplied by 0.22. Now this is the moment of truth. What we need to find is that our Vn value is going to be greater than or equal to 14,715, and so that's what should show up in this calculator. So if I press enter, what I end up finding is that Vn is equal to 79,134, and then what we're going to end up having for our final unit is this inches and this inches. If we multiply those out, that's going to give us inches squared. That's going to cancel with the inches squared underneath this fraction here. We're going to be left with a unit of pounds. And so now what we end up finding is, yes, this does pass the test. This is going to prove that the W12 by 16 beam can withstand that 14,715 pounds of shear force. It can actually withstand 79,134 pounds, which is greater than this value. So far, the W12 by 16 has passed all of our checks. Now the last thing that we need to end up checking is deflection. So we've got to first determine what the max deflection is, and then we've got to calculate out for this W12 by 16, how much deflection are we going to end up having. Now if I go back to these notes, we can end up looking at this. Now within here, they end up talking about the max deflection, right? So let's go ahead and let's look at this. So max deflection here. So max deflection. So for roof members, the deflection limit supporting plaster ceilings, it's going to be these values right here. So that's L divided by 240 for the dead plus the live load. So that's whenever we sum those two values. Now for just the live load itself, we got to take L divided by 360. Now keep in mind, L is expressed in feet for our problem, right? For deflection, we want to end up with a unit of inches, and so we've got to convert that from feet to inches here for these calculations, okay? And so now we're going to end up going through here and we're going to calculate out that max deflection. So let's go ahead and let's actually do that. So max deflection, or the deflection limits, is what we'll put down. So these are the deflection limits. So deflection limits, we'll kind of make this look a little nice and neat. We'll put this little guy around here so that we really emphasize, hey, that's what we're calculating out in this section. So this is for a plaster ceiling, and so we're going to go dead plus live load, right? And so now that max deflection is going to be equal to L divided by 240. Now, just as we said, it's 18 feet for the spacing of the span of our beam. We need to convert that to inches. So if I do multiply that by a conversion factor, 12 inches per foot, we're going to find that these cancel. We divide this by that 240. And so now this is going to be 18 times 12 divided by 240. And what we're going to end up finding for this is that we end up with 0.9 inches. So we got 9/10 of an inch max deflection, right, that we can have. Now, if it ends up being greater than that, then that means that we've got to get a beefier beam, right? We got to choose a beam that's going to have a greater moment of inertia. That's what we're going to end up finding out here. So we've got this dead and live load here. Found that out. Now let's calculate that out just for the live load. Now this is something that we're going to have to be careful with too. So the dead and live load, you know, we have this max deflection. Now just for the live load, we've also got to determine that max deflection. And so we're going to have L divided by 360. And so that's just straight from these notes, right? So L divided by 360 for the live load. So that's where I'm getting that. And what we're going to do again is we're going to take our 18 feet. We're going to convert that to inches. So 12 inches per 1 foot. So our conversion factor, those units cancel, we're left with inches. We're going to divide this by 360. Now we can take that 18 times 12 and then divide that by 360. We're going to end up finding for our live load, we can only have our beam sag down 0.6 inches for that. So 6/10 of an inch. Okay. So now that we know these limits, let's actually find out what is the max deflection. And so that's what I'm going to do here. I'm going to put this guy right there. Now, just as we've done in the past, we want to end up looking at our equation sheet. Now, what we're going to do first is we're going to calculate out the max deflection for our live load. And so the deflection equation that we're going to end up using is going to be max deflection equals, and we're going to put down the 5WL raised to the 4th power divided by 384 multiplied by E multiplied by I. Okay, now this is going to be occurring at the center of the beam where we're going to have the max deflection. So that's just going to be the sagging of the beam. And so now what we can do is we can put 5. Now we're going to multiply this out. Now what I want to specify here, this is the live plus dead load, right? And so we're going to find out based off of the uniformly distributed load of the live plus dead load, which was equal to that 10,000 or 1,090 pounds per foot, right? We're going to find out how much this is actually going to sag down. If it exceeds 0.9, then we got to get a bigger beam or a better beam. So we're going to multiply this by the length of the beam, which is going to be that 18 feet. Now keep in mind here, one thing that I did that I'm going to end up Xing this out, I'm going to cross this out. We need to do 5 times 10, 90 pounds times divided by feet. Now, since this is deflection, we got to make sure we don't make this silly mistake. We got to make sure everything is in inches, right? So now what I'm going to do is I'm going to actually convert this using the conversion factor, 1 foot, 12 inches. That way my feet units will cancel, we'll be left with inches there. Now I gotta do the same thing for the length. If it's 18 feet, what we gotta do is we're gonna multiply this by the conversion factor, and 1 foot, there are 12 inches, right? Now why did I put feet on the bottom here? It's because we wanna cancel these out, right? Feet on the top, so I put feet on the bottom for the conversion factor, we're left with inches. Now this needs to be raised to the 4th power. We're gonna divide this guy by 384 multiplied by E. E is the modulus of elasticity, or the Young's modulus. Now what that value is for steel, of these wide flange beams, we're using steel, so it is 29 times 10 to the 6th power PSI, pounds per inch squared. And so since we got inches down here, we got inches here, and so what we should end up doing is we should have all this cancel out. We should be left with just a value of inches. Now the modulus of elasticity, we got to be a little careful. I might be getting ahead of myself a little bit here by putting down the 103. What I want to do is I want to go ahead and go to this, and we're going to find that W12 by 16. So I'm going to scroll down. We're going to find the W12 by 16 because that's what we specified for the designation of this beam. And we've got an I value. Now we did it for the x-axis. We got 103. So turns out top of the dome, I did have that memorized. That was correct. 103. Now the unit for this, if I go back here, you can end up seeing this is for the x-axis. It's inches to the 4th power. So now that's what we're going to also specify here, inches to the 4th power. Now, in terms of these units, let's talk about the dimensional analysis of this. We've got an inch on the bottom here. We've also got square inches on the bottom here, right? We've also got inches to the 4th power. Now, if I take inches and I put that to the 4th power, that's going to be inches to the 4th power there. So that's actually going to cancel out with this guy down here. Now, if we have 1 over an inch divided by 1 divided by inch to the squared, you'll remember if you end up having the case like this where it's inches squared here, that's actually just equal to inches squared up on the top, right? Now this is the case where it's 1 over an inch, right? So now in this case, let's go ahead, let's just exit this out. If I multiply this by 1 over an inch here, what we're going to end up finding is that this is going to basically be the case of just square inches divided by an inch, right? So now that inches cancels with this. We're going to be left with just a unit of inches, which is what we want. And so that's the dimensional analysis of this. So we got the max deflection, that's going to be equal to a certain value in inches. And so now what I can do is I can take 5 times 1090, divide that by 12. Then what we can also do is multiply that by 18 times 12. We can raise that to the 4th power. We're going to end up getting that very big value. I can now divide this by, remember we want to ensure that we are putting on here we're going to put on here these brackets, right? So we want to make sure that these parentheses are put in here. So we're going to put in here 384 times 29 times 10 to the 6th power, and then that multiplied by 103. And what we're going to end up getting for this value is we're going to end up finding that it is going to be equal to 0.86. And so now we got 0.86 inches. Now in terms of this max deflection for that live and dead load, what we ended up determining, hey, for the dead and live load, we can have up to 0.9 inches of deflection. And so since this is less than 0.9 inches, the W12 by 16 will give that a check mark in terms of that test. However, we do need to calculate it out as well for the dead load, right? Or sorry, just the live load, my apologies. That's a mistake there, so live load. Okay, so now our live load, if we go in here, we got some changes we gotta make. Delta max is gonna be equal to 5 times now W for just the live load. We'll end up finding that that was equal to that 790, right? So that's equal to 790. And so if we go back to this initial problem statement here, we'll end up seeing that the live load was equal to 790, right? So now we're gonna end up putting that in here. So W is gonna be 790 pounds per foot. Now remember, we've gotta convert that from feet to inches. So everything needs to be in inches for deflection. Those feet are going to cancel. We're going to be left with pounds per inch. Then we're going to multiply this by L. Now L in this case was still 18 feet. Now we need to convert 18 feet to inches. 1 foot goes on the bottom, 12 inches goes on the top. Feet cancel. We're left with inches there. This is to the 4th power. We're going to divide this by, same thing here, 384 multiplied by the modulus of elasticity. For steel, that is 29 times 10 to the 6, and that is in pounds per square inch. We're going to multiply that then by the moment of inertia for this W12 by 16 beam. Moment of inertia is going to be 103 inches to the 4th power. So now we've got this. Once again, it's going to be the case. This inch is going to be the 4th power. It's going to cancel with this guy. This one's going to cancel with one of these. Our pounds are going to also cancel here. We're going to be left with just a value in inches. And so now what this test, what we need to end up calculating out here is that it's going to be a value that's less than 0.6. If it is greater than 0.6, then guess what? We cannot use the W12 by 16 beam. This one's got to go, and we got to find one that's beefier, right? So if we calculate this out, what we're going to end up determining here is that it is equal to, sadly, 0.63 inches. Now, in terms of 0.63 inches, is that less than 0.6 inches? No, it is not less than that. And so we've got to revise our choice for this, okay? So thankfully, it passed a lot of these tests. The W12 by 16 was not it though, because in terms of that live load, we need to have 0.6 inches or less of deflection. We had 0.63. So we're going to revise our decision. We're going to revise it, and we're going to end up finding something else that's going to work. Now, whenever we look at this equation for the deflection, what we end up finding is that it is equal to 5 times W multiplied by L to the 4th, and then we divide that by 384 times E times I. Now for this problem, W is going to have to remain the same, L is going to have to remain the same, E also remains the same because that's the modulus of elasticity. Now however, I, that is dependent, so that's dependent on beam. Right? That's dependent on the beam that we're looking at. And so now what we just found is that this 12 by 16 beam, the I value for X, the axis XX, was 103. Now what we need is a value for I that's going to be greater. Now if I look at this 12 by 19, I end up finding that it's 130. Okay? Now keep in mind, what we were thinking about beforehand is, you'll remember, we ended up saying, hey, one of the other possible solutions is that we could end up using a 10 by 17 beam. Now if I go down here to the 10 by 17, we can end up seeing this IX value is 81.9. Now, is that going to end up working, the 81.9? If we go back up here, this was 103, right? No, it's not going to end up working. So 12 by 19 has 130, which is going to be a higher moment of inertia, which means that it's going to cause less deflection. And so what we're going to end up doing is we're going to try the W12 by 16 beam here, okay? Now, in terms of that W12 by 16 beam, we can end up also looking at some other values here. W12 by 16, let's bring it up, W12 by 16. So we can also look at, for this W12 by 16 beam, we can look at the depth, we can look at the thickness as well, and we can compare that. As you remember, in terms of the other beam that we were using, so, oh sorry, we're going to try the 12, my apologies, little mistake there, 12 by 19. That's the one that we're going to be using. Now, if you look at this, in terms of that area, the depth is 12.16 and the thickness is 0.235. And so that's going to actually do a better job in terms of creating a higher nominal shear force. Because as you'll remember, the nominal shear force is equal to 0.6 times Fy times AW, where AW is equal to D multiplied by TW. So since we're choosing the 12 by 19, we're actually gonna have a higher shear force. The shear force already passed with the 12 by 16, so we're good in terms of that. In terms of that moment as well, if we end up looking at our calculations for that moment, it's equal to Fy times Zx, where Zx is that plastic modulus. If we end up looking at the plastic modulus of a 12 by 19 in comparison to 12 by 16, we're going to also end up finding that the Zx value is greater too. So we're going to for sure be passing the test for the nominal moment as well. Okay. So all we're going to end up determining from this is just that moment of inertia calculation for the max deflection. Okay, so we're gonna end up using that 130 value. Okay, so let's go ahead and let's take note. I, in this case, is going to be equal to 130 inches to the 4th power now instead of the other one. So let's go ahead, let's do this calculation. Now, once again, what we've got to determine is that just for the live load using this 12 by 19 beam now, which has this inertia, we need to end up finding that this total max deflection is going to be less than 0.6. If it's less than 0.6, great, we can use the 12 by 19 beam. So let's go ahead, let's do this. So 5 times W L to the 4th divided by 384 times the modulus of elasticity multiplied by that moment of inertia. So it's 5 times, as we said before, the live load that we need to support is 790 pounds per feet. Now remember, we want inches, everything in inches instead of feet. So if I convert this using conversion factor, I'm gonna put feet on top, 12 inches on the bottom, because 12 inches go into 1 foot. We can cancel those. We're gonna multiply this by the length. Now this is 18 feet. It's the length of this beam. Now what I want to do is I want to convert this from feet to inches, right? Now 1 foot, there are 12 inches, feet cancel with feet. This is raised to the 4th power. We divide this by 384. The modulus of elasticity for steel. Once again, modulus of elasticity for steel, that is going to be equal to 29 times 10 to the 6th, and that is going to be pounds per square inch. And we're going to multiply that by our new I value, which is 130 inches to the 4th power. And whenever we punch this into the calculator, we're going to end up finding a value, and hopefully that value is going to be pretty solid, because if it is pretty solid, then that means that we found the correct beam that we need. Whenever we calculate this out and we punch this in, we end up getting that this is equal to 1/2 of an inch here. And so because it is 1/2 of an inch, that is less than that deflection limit of 0.6 inches. And so we end up finding that that passes, and the W12 by 19 beam does end up working, right? And that's because this is going to deflect about 1/10 of an inch less than that limit that we have. So we can end up going for that W12 by 19 beam. The plastic section as well, ZX for the W12 by 19 beam is greater than that of the 12 by 16. We also ended up finding out that the depth as well as the web thickness was also greater in the 12 by 19 beam. And so it is sufficient to say that we can safely support the bending moment and shear, as well as we will not exceed the deflection limits if we use a 12 by 19 beam. Hope that was helpful. Thank you all so much for watching. If you got any questions, comments, concerns, drop them in the comments. As always, like and subscribe. Catch y'all later in the next video.